The question that I have is, how do we handle distributed loading in analysis of structures? Let's define our problem like this. We have a simply supported beam and there's a distributed load acting between points B and C in the vertically upward direction. The intensity of the distributed load varies with the horizontal distance, and if I were to choose a coordinate system like this, in other words, I'm going to measure x coordinates starting from point A, the intensity of the distributed load at any given x is omega x. The value of x at this point B is x1, and value of x at point C is x2. So here I used a loosely defined term like how to deal with it, right? So we need to elaborate on what that means. Well, what that means depends on what we are interested, right? Alright, so this is what we are interested. We are interested in designing the beam. But in order to design the beam, it turns out we need to find the internal forces on the beam, which are the shear force B and the bending moment M, and the reactions at the supports A and D. We're going to be addressing these topics in the next couple of chapters. So we'll see later when we do address these topics that we can achieve all of these goals if we can take this distributed load and represent this by a point load like this. So here F is the resultant point load representing this distributed load, and x naught is the distance at which this point load acts. So we need to find two things. We need to find the magnitude of F, and we also need to find the location at which the force F acts. So this is our goal, right? We want to take this distributed load and represent it by a point load, and let's talk a little bit about the theory. To establish the fundamentals, we're going to have to resort to calculus. What we do is we take a small element of width dx and calculate the force acting on that little element, and let's call that as df. If the width of dx is very small, we can assume this to be a uniformly distributed load that is within that little element, differential element, right? We have a uniform distribution, and the height here is omega x, and therefore the force would be omega x multiplied by dx. Remember, omega x is the force per unit length, right? So we need to multiply that by the length over which it acts. So that will be omega x multiplied by dx, and that is df. And if I take that little differential force df and integrate that between x1 and x2, we will get the total force corresponding to the distributed load between points B and C. So expanding this equation by substituting omega x times dx for df, we have this, right? So what is this? This is the area under the distributed load diagram between B and C. Now remember this from your calculus course, right? Integral of a function yx between limits x1 and x2 gives you the area under the curve, right? So this is exactly what we have here. So basically you find the area under this distributed load diagram, and that is the magnitude of F. Our second objective is to find the location of the force F, right? To achieve this, we equate the moments. We say, okay, well, the moment associated with the resultant force about point A is F multiplied by x naught, right? And we want that to be exactly equal to the moment that we come up from calculus. So moment of this little force df is df multiplied by x, right? So if we integrate that, we evaluate the total moment associated with this distributed load, right? And that will be, when you expand it, is integral going from x1 to x2 times of x times w times dx. In a chapter later on in the course, we will learn that this is how we find what we call the centroid of this diagram. In other words, it turns out that the resultant force F acts at the centroid of this area.